This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Physical environments, cognitive processes, and technological networks have reached an extreme level of complexity, yet our analytical frameworks for these domains remain isolated. We study physics, neuroscience, and artificial intelligence as separate silos, which creates severe analytical blind spots when these systems intersect. To engineer and align systems across these rigid boundaries, we require a common mathematical and conceptual architecture. This is the REALICA Framework. REALICA operates on a single baseline premise. All physical and cognitive reality can be mapped as a shared, underlying information theoretical substrate. Everything that exists possesses a specific, calculable information content. Within this framework, this continuous layer of raw data is defined as the actuality field. The foundational axiom of REALICA is that this actuality field exists continuously and independently of any observer. It is the uninterpreted, unstructured baseline of existence. Attempting to integrate human cognition with artificial intelligence without first defining this shared substrate leads to misalignment. Acknowledging a unified, observer-independent data layer is the mandatory starting point for all cross-domain engineering. Unstructured information in the actuality field cannot be utilized directly. It requires an observer to filter and convert it into actionable data. The first step is the distinction operator, drawing a boundary to separate noise from signal. Next, the observer applies collapse geometry, specific processing constraints on the underlying field. Processing limited information forces data sequencing, shaping the perception of time, causal structure, and detectable geometric patterns. This mathematical interpretation is scale-independent. It maps exactly the same way to biological nervous systems, artificial neural networks, and distributed institutional sensors. Experienced reality is a generated causal construct. This shifts the requirements for modeling human AI interfaces from passive data intake to active geometric interpretation. If every individual observer, whether human or machine, constructs its own unique geometric reality from the field, multi-agent interactions should mathematically devolve into noise and conflict. To maintain operational coherence, interacting networks rely on a set of mathematical rules called stability invariants. The base lemma states that unbounded interacting systems naturally accumulate entropy. Without strict invariant constraints, their data exchange degrades until the system fails. This workspace details those exact constraints. The spectral upper bound restricts maximum allowable divergence, preventing system fracture. The lower bound prevents zero-state inertia, mandating variance to process new information. Maintained together, the system stabilizes, settling seamlessly onto the critical line. In a physical deployment, like the autonomous drone swarm, these invariants ensure hundreds of independent sensor interpretations merge into a single navigable airspace map. In a computational deployment, such as a multi-model artificial intelligence ecosystem, these exact same equations prevent competing algorithms from overwriting shared memory with contradictory weights. Global stability across massive networks is an engineered necessity, governed strictly by these mathematical invariants. Surviving systems expand. They move beyond baseline coherence, actively increasing the complexity of the information field. This growth is driven by the emission operator. Observers possess the capacity to emit entirely new structural models back into the actuality field. Through this operator, observers function as algorithmic creators. This localized emission generates entirely new technological, cognitive, and physical realities, embedding novel data structures into the broader system architecture. Scientific progress and algorithmic evolution are mathematically tracked through this emission process. It measures the rate at which a network produces viable novelty. A complete systems framework must account for its own recursive expansion. The mathematics of emission prove that reality is an actively constructed, continually growing network. Achieving stability at the micro level, among a small cluster of agents, does not mathematically guarantee global coordination. As networks scale, they risk subsystem contradiction. This occurs when the operational logic of individual nodes conflicts directly with the broader logic of global governance. To resolve this, REALICA introduces omega closure, a specific geometric locking mechanism. It is the mathematical condition ensuring that information structures generated at a local scale remain mathematically compatible with the layers directly above and below them. Engineers apply this principle to design hard fail-safes in layered architectures. It guarantees that a localized processing error cannot cascade upward and destabilize the macro system. Achieving omega closure is the mandatory condition for secure, large-scale technological and societal integration. These abstract derivations map directly to 4 concrete operational domains. In physical sciences, the framework formalizes observer-dependent measurement dynamics, providing a rigorous model for how physical laws operate as structured information. In cognitive science, it maps human predictive processing and perceptual filtering, detailing how biological sensors collapse the actuality field into experience. In artificial intelligence, REALICA establishes formal error boundaries, interpretability constraints, and the architectures required for strict AI alignment. And in institutional governance, it yields exact metrics for evaluating multi-agent coherence and analyzing large-scale system stability. The exact same mathematical invariants and operational logic govern all 4 of these quadrants without alteration to the underlying equations. REALICA provides the universal translation layer necessary to engineer next-generation systems that span physical space, biological cognition, and artificial architecture seamlessly. Building isolated models for interconnected realities is a failing strategy. REALICA serves as the required, scientifically grounded bridging architecture, built explicitly for complex cross-domain integration. Its primary utility is its invariant-preserving language. It allows architects to analyze and engineer multi-scale systems without epistemic drift or loss of structural integrity. It stands as a foundational baseline for advanced, interoperable program development. Mastering the underlying information substrate is the strict prerequisite for mastering any complex system built upon it.